Welcome to NeuralTensors. Today we are taking a deep dive into the math behind linear regression, an essential foundation in machine learning. We'll start with the basic setup, define our model and cost function, and work through the optimization process using gradient descent. So let's get started. Consider a data set where we want to predict a person's weight based on their height. In this example, we have one feature, height, that is x, and one target variable, weight, that is y. We assume a linear relationship between these variables, which means we'll model the data with a straight line. In linear regression, we assume a linear relationship between the input x and the output y, which is represented by the equation y equal to w0 plus w1x, where w0 is the intercept and w1 is the slope or weight. This is the weight of the input variable. These two parameters determine the position and angle of the line that best fits the data. Our model is defined by y hat is equal to w0 plus w1x, where y hat is our model's predicted output. Here w0 and w1 are the parameters we need to adjust to minimize the difference between y hat and the actual values y. To quantify this difference, we look at the error for each data point I, defined as ei is equal to yi minus yi hat. When we square these individual errors and take the average, we get the mean squared error, that is MSE. So here's the formula for MSE. Here, yi is the actual value, yi hat is the model's predicted value, and n is the total number of samples in the data. The mean squared error essentially tells us how well our model fits the data. A smaller MSE indicates a closer fit, and our goal in linear regression is to find the parameters w0 and w1 that minimize this cost function. Gradient descent is an optimization technique that iteratively adjusts w0 and w1 to minimize the cost function. Imagine MSE as a 3D surface where each point represents a particular pair of w0 and w1 values. Our goal is to reach the lowest point on this surface. To move towards this minimum, we need to calculate the slope of MSE with respect to both w0 and w1. These are the partial derivatives of the cost function. So here's the partial derivatives of MSE with respect to w0 is equal to minus 2 by n summation 1 to n yi minus yi hat. And in the same way, here we have the formula for w1. Partial derivatives of MSE with respect to w1 is equal to minus 2 by n summation 1 to n yi minus yi hat times xi. And we get this simply by using basic calculus. Here we may have to use chain rule as well. After calculating these gradients, we update w0 and w1 by subtracting a fraction of the gradient. This fraction is known as learning rate, denoted as alpha. So here we have the updated equations. w0 is equal to w0 minus alpha times partial derivatives of MSE with respect to w0, and w1 is equal to w1 minus alpha times partial derivatives of MSE with respect to w1. The learning rate alpha controls the step size during each update. Choosing an optimal alpha is crucial. If it's too large, we might overshoot the minimum, and if it's too small, the convergence can be very slow. This plot demonstrates how we start with the initial random values for w0 and w1, which yield a high error, and through iterative updates gradually arrive at the optimal values that minimize the mean squared error. On the left, we see the scatter plot of our data points, which represents the relationship between our input x and output y. Initially, we start with a randomly chosen line that doesn't fit the data well, as shown by its slope and intercept values, w0 equal to 0 and w1 equal to 0. With each iteration, gradient descent adjusts W0 and W1 to reduce the error. Each line drawn represents the regression line at the specific iterations, showing how it gradually moves closer to fitting the data. Notice how the line moves closer to the data points over time, capturing the underlying trend more accurately as it approaches the optimal fit. On the right, we see the mean squared error plot over the iterations. Initially, the error is high as the line is far from the fitting data. But as we proceed, MSE decreases with each iteration, indicating that the line is better aligning with the data. This steady drop in MSE signifies that our parameters W0 and W1 are converging towards the value that best represent the data. By the end of our iterations, we have found the optimal values of W0 and W1 that minimize the error, represented by the lowest point on the MSE curve and the final line on the left plot. This final line is our model's best fit to the data, with the lowest achievable MSE for this linear relationship. After completing the gradient descent process, we reach the values for W0 and W1 that minimize the MSE, that is mean squared error, and these are the most appropriate parameters, giving us a straight line that best fits our data with the lowest possible error. In other words, we have found the line that captures the relationship between height and weight in our dataset, and using which we can predict the weight for any given height. In real applications, we often have more than one input variable, like predicting weight based on height, age, and diet. In this case, our model becomes a multivariable linear regression, which can be represented by the equation y equal to W0 plus W1x1 plus W2x2, so on up to Wn xn, where x1, x2 up to xn represent different input variables and each has its own weight Wi. Gradient descent can still be used for multivariable linear regression, adjusting each weight Wi based on the gradients calculated with respect to each input variable. And that's the mathematical foundation of linear regression. We have covered the model equation, cost function, and the gradient descent, along with an introduction to handling multiple inputs. So if you found this video useful, please give a thumbs up, subscribe to my channel, and turn on notification for more machine learning related contents. Thanks for watching. Have a nice time.